Okay, what I'm going to do now is I'm going to work an example where we're going to find an optimal portfolio, or we're going to find optimal weights for a portfolio made up of 8 stocks that everyone has probably heard of. Okay, we're going to do this. This is the fourth case that we're working on. We're going to maximize this ratio. This is the expected return of the portfolio relative to the standard deviation of the portfolio. I'm going to use the standard deviation of the portfolio instead of the variance of the portfolio just for personal preference here. And I'm going to basically maximize this function. It's made up of 8 individual stocks subject to the weights of each of those 8 stocks summing to 1. Okay, let me explain. I'm going to use the matrix algebra. We talked about this last time in the last video. So the expected return is going to be the weight vector. Let me explain what the weight vector might look like. The weight vector is a vector of weights for each of the 8 assets. Here I have it in general notation. I have n weights in my portfolio. In this actual case that we're going to be working, n would be equal to 8. So I have the weights of each of the 8 portfolios. I have a return vector. These are the returns for each of the 8 stocks. Okay. And then this here is the variance covariance matrix. Let me explain what this is. So in the diagonal of the variance covariance matrix, we have the variances of each of the 8 stocks. And then in the off diagonal, we have the covariance. So sigma subscript 1, 2 represents the covariance between asset 1 and asset 2. So in the first row, second column, we have the covariance between the first stock and the second stock. In the first row, third column, we have the covariance between the first stock and the third stock, and so on. In the eighth column, we have the covariance between the first stock and the eighth stock. So in these off diagonals, I've created the covariances, and in the diagonal of this n by n matrix, or in this case an 8 by 8 matrix, I have the variances of each of the assets. Okay, so this is where we're going. I pulled some data. Okay, here we have for 2019, we have daily returns for Microsoft, Facebook, Google, Apple, Walmart, Amazon, Netflix, and Tesla. All right, and what I'm going to do here is I'm going to basically go about creating all of the inputs we need. All right, I'm going to create all of the inputs that we need in order to solve this problem here. Let me see if you can see this. I don't want to lose sight of what we're trying to do here, so let me bring this over. Okay. All right. So let's first just get some statistics here. I'm going to grab the mean of each of these stocks, the standard deviation of each of these stocks, the variance, and I'm going to put together this ratio, the objective function, the ratio that we're trying to maximize here. Okay, this is easy enough to do in Excel. I'm just going to say equals average. Highlight that column there. So I've got the average of column B. Drag that over to get all of the averages, or the mean return, mean daily return for each of those stocks. I'm going to do the same thing with standard deviation. Okay. As well as the variance. And notice that I want the sample standard deviation and the sample variance here. All right. And then of course the ratio is just going to be equal to the mean divided by the standard deviation. This is my objective function that I'm going to try to maximize here in a second. Okay. All right, so I just have some statistics. Now what I want to do is I want to create the variance covariance matrix V. And so what I'm going to do here is I'm going to, let me just type these ticker symbols in. This is going to take you quite a bit of time to do on your own. But what I want to do here is I want to create this variance covariance matrix. All right, that means I want to create in the diagonal the variance, the variance of each of the stocks in the diagonal of this matrix. Okay, just give me 1 second to do this. Getting close. Okay, so I got the variances of each of the assets, each of the 8 assets in the diagonal. And in the off diagonal, what I'm going to do is I'm going to calculate the covariance. Okay, I'm going to calculate in column 2, row 1, I'm going to calculate the covariance, that's the sample covariance, between the first stock and the second stock. Let me go in and lock these here. Okay, so here's the covariance of the first stock and the second stock. Because I've locked that first cell, I can drag this over and create the covariances for each of these pairs of stocks. I'm going to do the same thing here. This is going to be the covariance between the second stock and the third stock. Okay, I'm going to lock that cell again. And then I'm going to drag this over here. And I'm basically going to create the covariances. Here would be the covariance between the third stock and the fourth stock. Here would be the covariance between the second stock and the first stock, the third stock and the first stock, and so on. So I'm going to populate this variance covariance matrix. I've actually already done this. Okay. So here's the variance covariance matrix. Now what I'm going to do is I'm going to go over here to the side. So again, the diagonal consists of the variances. Okay, there's my variance of Microsoft, my variance of Facebook, my variance of Google and Apple, and so on. I've populated the rest of the variance covariance matrix. Now what I want to do is I want to create a weight vector for Microsoft, Facebook, Google. What I'm going to do here, this is a little trick that will help you make sure that you're doing this right, is when I create my weight vector, I'm going to put all of my weight in Microsoft, or in the first stock. Okay, so I'm going to put all of my weight in that first stock, because then when I do the matrix algebra, okay, when I do all of the the matrix multiplication, all this matrix stuff, I'm going to be able to quickly check to see if it's correct. Okay, my return vector here is going to be equal to, now this is important, what I'm going to do, give me a second, let me go full screen here. What I'm going to do here is I'm going to highlight these mean returns for each of those 8 stocks. Let me copy them and let me paste them. I'm only going to paste the values here, and I'm going to transpose them so that they're in vector form. Okay, so here's the mean return of Microsoft, the mean return of Facebook, the mean return of Google, Apple, all the way down to Tesla. Okay, so I have my variance covariance matrix, I have my weight vector, and now I have my return vector. All right. Let me do something else. Let me introduce the constraint. Recall that my constraint is going to be, I'm going to require that the sum of all of these weights to equal 1. Okay, so if I scroll over here, my constraint in this cell is going to say sum of all of these constraints, and then when I identify my constraint, I'm going to require that this cell L271, is going to equal 1. All right. Let's do this matrix multiplication here. So what I'll do is let's first calculate the expected return of the portfolio. Recall that the expected return of the portfolio is this weight vector transpose. So right now this is an n by 1 vector. I need it to be a 1 by n vector, so I'm going to transpose that, and I'm going to multiply it by the return vector. Okay, the function in Excel is mmult. So I'm going to do some matrix multiplication where I transpose the weight vector. Now make sure that you don't grab that constraint. Just grab those 8 cells there. And I'm going to multiply that by the return vector. Okay, so you can come up here and look at the formula. Matrix multiply the transpose of the weight vector by the return vector. Now when I hit enter, it gives me this error. Okay, and the reason that it gives me this error is whenever you do matrix multiplication, in order for Excel to solve it, and I don't know why, you're going to have to hold down Control Shift, and then when you press enter, it will give you the product of the matrix multiplication. So here, notice all of my weight is in Microsoft, and therefore I know that the expected return of the portfolio should just be equal to Microsoft's return. That's one of the reasons why I put all of the weight into one stock. Okay. To calculate sigma of the portfolio, this is going to be a little messier. I'm going to take the square root. Okay, I'm working over here. I'm going to take the weight vector transpose and I'm going to multiply it by the variance covariance matrix, and then I'm going to multiply it again by the weight vector that isn't transposed. So I'm going to say m mult, and I'm going to do another matrix multiplication here. And inside the second matrix multiplication, I'm going to take the weight vector transpose times the variance covariance matrix. This transposed vector will now be a 1 by n vector times an n by n vector. That's going to give me a 1 by n product. So let's transpose the weight vector. And then I'm going to highlight this entire variance covariance matrix. Okay, so I've got the matrix multiplication of the transposed weight vector times the variance covariance matrix, and then I'm going to hit a comma, and I'm going to multiply this by the weight vector again. Okay. Let me fix this actually. You got to be careful with these. So look, I matrix multiplied the transpose of the vector. Okay, that should work. Hit Control Shift Enter, and I get a sigma p of 1.25%. Let me come over here, and the standard deviation of Microsoft, which by the way my portfolio is completely made up of Microsoft at this point, is only 1.25%. So that it looks like it works. Okay. So next, what I'm going to do is I'm going to calculate that ratio. This is the objective function, and it's just going to be equal to the expected return on the portfolio divided by the standard deviation of the portfolio, 0.1508. I'm going to scroll over here and verify that that's the same as Microsoft's. Okay, so it looks like I'm on track here. All right. So I've been able to do all the matrix multiplication that I need to do. Now what I'm going to do is I'm going to introduce solver here. The objective is to maximize the objective function, which is this cell, subject to the constraints equaling 1 by changing these weights. All right. If I go to the Data tab, there should be a solver tool pack here. This is a solver tool. If you don't have that, click File, go to Options, click Add-ins, hit Go, and you should click that solver button and hit OK, and it will show up underneath the Data tab in Excel. Okay, so I'm going to click Solver. I'm going to set my objective function. My objective function is going to be this ratio. I want to maximize that objective function by changing which cells. I'm going to highlight my weight vector. So I'm going to change those cells. Okay, and now it says subject to a constraint. Let me add the constraint. My constraint is this cell L271, must equal 1. Okay. All right, so my objective function is that ratio. I'm maximizing that objective function by changing the weights subject to my constraint. Now notice something here. This thing is checked by default. This makes all unconstrained variables non-negative. This is important. So if I have this box checked, that means that I can't sell short. All right? That means, think about it. If I'm optimizing or maximizing my objective function subject to this constraint, it might tell me to short one of these particular stocks, use the proceeds from that short sale, and invest in another particular stock. Does this make sense? So what I'm going to do here, I'm going to make those variables, the unconstrained variables, non-negative, which means I'm not going to allow for short selling. All right. We can allow for short selling here in a second. Let me go ahead and solve this. It's going to take a second. And look at what happened here. So when I solved this, when I maximized that objective function, it told me to put 15%, almost 15.5% of my weight in Microsoft, about 5.7% of my weight in Facebook, 34% of my weight in Apple, and almost 44.5% of my weight in Walmart. Okay, that sums to 1. Those weights sum to 1. And what I've done here is I've created an optimal portfolio. Look, this ratio, 0.19, okay, if I were to go over here and look at all the other ratios for all of the individual stocks, that ratio is higher than any of them. In other words, there is no other combination of weights that is going to get me a higher ratio. I hope you understand that. All right. What else did we do? Just going to Google some stuff here. Look, what we've done here, this is the Markowitz efficient frontier, right? And on that Markowitz efficient frontier, we have found the portfolio. There exists infinite number of portfolios because I can change those weights. We have found that portfolio in the most northwest quadrant, right? We found that portfolio in the most northwest quadrant, okay? So these are the weights that we would use. Again, we're not allowing for short selling. The objective is to maximize that ratio. I'm going to cancel this out. Okay, let me go in here and do it again, and let's this time uncheck this box and allow for short selling. Sometimes we get really screwy answers here. Let's see what happens. Not too screwy. But look at what happened. We're going to short Google. We're going to short Amazon, we're going to short Netflix and Tesla, and we're going to use the proceeds from those short sales to buy more Walmart, more Apple, more Facebook, and more Microsoft. Notice what happened. My ratio in the last, when I didn't allow for short selling, was 0.19, I think. I can't remember. But right now it's almost 0.23. So if I allow for short selling, that's actually going to increase my ratio up to 0.23. All right? That's a significant jump in the ratio of my expected return on the portfolio to the sigma of the portfolio. Okay, so here's another exercise where when we allow for short selling, we can see that the objective function is maximized even to a greater extent. Let me cancel this out again. While we're here, let me show you one other thing that we can do. All right, some of you are crazy risk averse. All right. Notice something here. What I'm going to do here, before we do anything else, let's scroll over and look at the standard deviations. Okay, you can see those standard deviations. In fact, what I'm going to do, well, let me get out a solver here real quick, and let me highlight this row here of standard deviations. And let's just eyeball and see which one had the lowest standard deviation. This might not come as a surprise, but it looks like Walmart is the least risky of all the stocks. Tesla, on the other hand, had the most volatility. All right, so Walmart has the least lowest standard deviation, the least volatility, 0.009, so 0.9%. What I want to do now is let's go back to Solver, and let's, instead of finding the optimal portfolio, let's find the portfolio where we change the weights that minimize the standard deviation of the portfolio. Okay, so instead, now my objective function, instead of being the ratio, is just going to be my sigma of the portfolio, L274. Let's minimize that by changing the weight vector subject to the constraints. Let's not allow for short selling, and watch what happens. When I solve this, look at what happened. This is, to me, I think this is interesting. This is one of the reasons why I think finance is so interesting. Because of the structure of the covariances in this variance covariance matrix, because of the structure of the covariances, we were able to create a portfolio of 8 stocks. We're putting in 7.7% in Microsoft, 4.3 in Facebook, 5.5 in Google. Notice that most of this is going in Walmart. All right, we're even putting some in Tesla, and Tesla had the most volatility. It had 3% volatility. So we're putting some of our weight in Tesla, and look at what happened. We've created a portfolio that has a lower standard deviation than any of the stocks that are in our portfolio. And that's a function of the structure of the covariance. The covariance is between the stocks, okay? So notice that we barely get a higher ratio than we had before, but the standard deviation of the portfolio is lower than any of those standard deviations. It's 0.82%. Let me cancel that, and let's go in and do this one more time, but allow for short selling here. So I'm going to uncheck this box, and when I click solve, watch what happens. I don't get much out of that, but it tells me to short. It tells me to short what stock is that? Amazon, right? And increase the weights in the other stock. It's about the same. So whether I short sell or whether I allow for short selling or whether I don't allow for short selling, I'm still getting a portfolio standard deviation that is much lower than anything else. So hopefully you understand what's happening here, not only in the model, but also intuitively. We're finding the optimal portfolio when we maximize this ratio subject to the constraint. We're finding the tangency of the portfolio that's in the most northwest quadrant. We're finding what's called the optimal portfolio on the Markowitz efficient frontier.